Uh, Hi everyone. I think all are in safe. Stay home. So in this current scenario, I thought that I should discuss on a topic which is very relevant nowadays, and so I am going to start my presentation and on electromagnetic levitation. Overcoming the effect of gravity has been a dream for generation of thinkers. Now you see that maglev train has come. So magnetic levitation train. So first Japan and Germany did started this work. Uh, Started this one. Now this common point in all this application is that lack of contract and thus no wear and friction, so frictionless. So obviously we need more speed to decrease the time from one platform to another platform. So this increases efficiency, reduces maintenance costs, and increase the useful life of the system. So, the recent advantages, notably in power electronics and magnetic materials, have focused this attention within the last decade on the application of electromagnetic suspension and levitation techniques to advanced ground transportation, magnetic bearings for rotating machineries, etc. So basically, electromagnetic levitation is using in transportation, magnetic bearings, and inductance heating also. So this use is not limited in scope actually, regardless of the fact that there is in fact a separate technology involved for each electromagnetic method. The whole subject is given a blanket title of maglev, means derived from the magnetic levitation, and is mostly used in a system of transportation that uses magnetic levitation to suspend, guide, and propel vehicles a floating or levitated condition. So now I am going to discuss uh, how to develop a prototype of electromagnetic levitation. So, so what is happening? So, uh, to develop a prototype, there are two type of challenges. That is the challenges in the practical aspect, the robustness of the setup, parameter uncertainties, this type of problems in practical aspect, and challenges in control aspects because the system is highly nonlinear system, the system is unstable system. So we have to go for higher advanced control strategies like SMCs, sliding mode controller, fit for our controller, etc. Now I will discuss on the three type of prototypes. First, design, modeling, calibration, fabrication of a spherical ball of 62 gram, because the spherical ball has a symmetric object. So center of mass its equilibrium point. That is the advantages of spherical object. But when the shape of the object change, means rectangular object, because in the practical real-time applications, practical applications, the shape is not spherical. That is the different type of shape. As the shape of a train is asymmetric shape. So we have to design control strategies for that kind of complex shape. So I will discuss first on the spherical object because it's very simple object in electromagnetic levitation. Very simple control strategies because center of mass from physics point of view, center of mass its equilibrium point. So if we can control the z direction, then it will be levitated at the operating point. No need to keep controller in the other directions x or y. or you no need to control the roll, pitch, yaw, etc. Because when the object in free space, there have tendency to roll, pitch and yaw, then XY direction control is also important. When the object in this free space means we are working against the gravitational force. So nature of the gravitational force is too much hazardous. Not like there is no fixed pattern of the gravitational force. So we'll have to identify that pattern, and then we'll have to design, and we'll have to apply the control strategy in such a way that the flux natures make aligned in a particular direction, in which direction we are trying to control it. So that particular pattern is very important, because the flux natures of this, and there have also leakage fluxes, there have some disturbances, there have some misalignment of the fluxes. This type of problems we have to face in the electromagnetic levitations. Now I am going to the uh, I want to show the on practical system such that you can get the idea. So now see, the 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 spherical object is floating at 60 millimeter operating gap, and you can see this is the operating gap. Okay, and this is the coil. Okay, this is the coil. So the coil, under the coil, the spherical object is floating, and you can see that in the horizontal there have one LDR and one bulb. So the property of the LDR is, when light intensity increases, the resistance of the LDR decreases. When light intensity decreases, resistance of the LDR increases. This property, this is the feedbacks we are applying. You see that there are only one sensor controlling the Z directions. There are no other sensors in X or Y directions to control the object. So only one direction is sufficient for the spherical object, because center of mass is equilibrium point. But when the shape of the object changes, then to keep the steel plate in the free space, you need to control the X direction, Y direction, and small effect will come from roll, pitch and yaw. That also should be taken care of. But the point is, for this object, you say that the coil is size is very much big and the shape of the object is very small. Because of that, you can see that flux will exit from the coil core, and it will go through the spherical object. Then there are no path actually. Okay, so we made the frame of the setup is steel, such that it can get a closed path, such that the flux can get a closed path. Otherwise, the leakage will be more. What is happening here actually? The leakage is more. Maximum fluxes are distributed in free space. It is not getting closed path. That's why it is the in this case what is happening, the coil is very big, generating fluxes, but very few fluxes are going through the spherical object. So this is the disadvantage of this setup actually. So now I am going to the main slide. I am going. Okay. So now next I will discuss on how to design, model, calibration, fabrication, controller design. So for levitation, designing the levitation prototypes, first point is to design, to choose the shape of the object. First, to say, suppose the shape is rectangular. Then second, to choose the weight of the object. Suppose it is fixed. Now we'll have to design the coil, because coil, suppose coil is like mother and object is side, so there should be relationship, a good relationship between the coil and the object, otherwise it will not be levitated. So first mass of the object is fixed, then coil is fixed. Coil design is very very important part of this levitation, because coil, actually coil is the actuator. Coil is controlling the current. Coil is balancing the gravitational force. So coil is the mother, so coil is doing is and everything. So coil is the actuator, so coil design is very very important. So and must remember that actuator saturation should not be there. Actuator saturation, there should be some precautions to avoid the actuator saturation. Now now what is the fast? The object is the fast, yeah, coil is the fast. From my point of view, that object is the first. Shape of the object and weight of the object is fixed first. If it is fixed, now we can go for the coil design. Now what is the number of turns, or what is the wire gauge, what should be the inductance at the operating point, should be the current rating of the coil. That is the most important parameters to, because already I told this is a mother, this is a child. If there have some imbalance between this, so controller will not act. So before that, so now coil is fixed, object is fixed, coil design has been done, excellent combination, yeah, combination between object and coil. Now we can go for the analysis, electromagnetic analysis, field analysis. So how flux is going, how flux nature, how much flux leakage is happening, what is the this type of inductance profile. Now third is the parameter evaluations. So parameters, many parameters are there: inductance air gap parameters, current air gap, force air gap. These are parameters. So we will get, once the coil is fixed and the object is fixed, now we can make the system a prototype. Now prototype is in our hand, and this prototype should be mechanical, true mechanical zero setup and spirit level accuracy setup. Because we are working against the gravitational force, spirit level accuracy is most important, and true mechanical zero is important, because from outside, if there have any flux enter into the setups, this will create instability. So from any kind of disturbances will come into the setup. This type of flux should not be entered in these setups from outside. Okay, so this setup actually mainly coil and object, and rest of the setup should be non-magnetic is aluminum, something like. So so the magnetic field should not create disturbance or hamper. And finally, what will the magnetic field, if enters from the outside, the system will become unstable. So these type of precautions we have to take. And we have find out that if the object is rectangular and if the object of C shape, for same coil, then many parameters will be changed, because flux patterns will be changed, inductance profiles will be changed, force air gap will be changed. So each and everything will be changed. When each and everything will be changed, then controller will be changed. So if the suppose object is fixed but shape is changed, weight of the object is same, but shape is small amount of shape is changed. Suppose flat to C, then use type of different type of parameters will come, and the analysis will be different, parameter evaluations will be different, modeling will be different, flux natures will be different, a controller will be different, and finally means whole will be. So if object is fixed, coil is fixed, so this is a fixed prototype for this fixed object. No other type of object of different shape or different weight will not be repeated in this setup. So this object is fixed for this setup. Now later I will discuss about a large rectangular platform of a system. So please see this. So this type of spherical object in the left side, there a spherical object is floating. You can see that one light bulb and one LDR is there. Okay, so we have put only one feedback in Z direction. No other feedback is required here. X direction, Y direction control is not required because center of mass equilibrium point. So only one direction control is sufficient for spherical object, but for rectangular object you can see they have a operating zone, x direction control, y direction control. There are lots of sensors placed in x direction, y directions, and that whole weighted gain and combinations of sensors has been used to control the rectangular plate at that operating point. One things I forgot to tell you, that we are working on the small signal model. Means we are not working in the average model. Small signal model means at a particular operating point. Suppose for the spherical object 16 millimeter and for the flat object 8 millimeter gap. So at 8 millimeter gap we have fixed this gap, that we will levitate this object at this gap only, 8 millimeter gap, no other gap. So we will model, we will design, we will control modeling and controller design, everything will be on that particular gap. That is the small signal model. Means though the system is non-linear, we linearize the model at that particular point and then we will design the controller. That is the. So if we want to go the in the average model, so we'll have to go sliding mode controller, because the system is highly nonlinear system, and system is unstable systems obviously, because one force is the upward directions and coil force is the upward direction and gravitational force is the reverse direction. So these two directions are actually in opposite direction, so it will be unstable system and nonlinear system, because the force at air gap profile is highly nonlinear, so it will attract immediately. So we will have to restrict this at the operating point. We will have to restrict the object by using highly advanced control strategies, such that it can make the system stable, otherwise it's a highly unstable system. So for this, and the please see that for the spherical object the coil size is very big, because here actually there are, here fluxes are not getting closed path. So what happening, the fluxes are entering exit from the core, and then it is passing through the spherical object, then it is going to the frame. Actually frame is the steel, actually that's why it kept steel, because such that it gets a closed path. Otherwise if it would not be in the frame should be aluminum, then it would not be levitated. Actually it will not get any closed path, so field will not be passed through the spherical object, so force will not be generated. But for this rectangular object, please see that for this flat plate, rectangular plate actually. So please see that C type of core is used. A number of turns, wire gas, width of the layer, inner layer, outer layer. That is the different parts. That's taken care of. So coil design is also very important in electromagnetic limits, because mother and child relationship should be best by the designer, such that it cannot create another. There have lots of problems, so it cannot add another actuator situation. So that's precautions should be taken care of. Now, feedback sensors. So, for the flat plate, we have used the LED phototransistors, and we have created a operating zone, free operating zone in free space. Operating zone. So, we already told you we are working on the average model. Sorry, small signal model. So, at the particular point when we will keep the object, that then the controller will start to work. In the other operating points, the controller will not act. That is the this is also a drawback actually. Nowadays best is various model, means non-linear controller, sliding mode controller, etc. So that is the advanced control system. If it's applied here, then it would be levitated at any point, which point we will keep a reference, and at that point it will be levitated. That is the another drawback. Now I am going to the mm, we're going to do the setup. Please see that first figure 3, there have the coil, big coil, and the object is very small. Already I told you that the rating of the coil is 1 ampere and required current at the operating point is 0.6 ampere. Actually the flux leakage is more in the spherical object, because it's not getting a closed path, though we have kept the frame as still it is not getting the closed path, so leakage is more. That's why maximum fluxes are distributing in free space, so it is not getting closed path. So obviously when leakage is more, inductance is very less, so force is obviously less. uh, now figure 4, please see that the whole prototype except coil and object aluminum made. So what is the advantage? Advantages is that it will not be affected by the outside flux, so it will not be affected. So that is called true mechanical zero. And spirit level accuracy means that against gravitational force the setup is at spirit level, means object will be at spirit level with the surface of the uh, earth. And the PC figure 5, there that's a C type of plate levitation, and figure C, please see that and one big PCB is there actually. Four object is placed at the corner of aluminum plate, and that full body is levitating. Full body of the four object are placed at a aluminum plate, and then this plate is levitating. So we need four independent controller, four independent feedbacks, four independent sensors. Everything is separate, and four required, because for full prototype we are levitating, where there are four steel plate are placed at four corner. And PCB is very important, because disturbance is the main important in levitation. So a small kind of disturbances, electrical or mechanical, make the system unstable. So if the circuit is not uh, well fabricated, yeah, not PCB, then what will happen? Small amount of disturbances, ripple, will cause the system unstable. This type of precautions we have to taken care of. So PCB is important for the circuit, such that no disconnectivity or electrical disturbances cannot make the system unstable. So this type of precautions should be taken. So electromagnetic levitations, and what is the problems in practical aspect and control aspect. So practical aspect, there are the problem the weight distributions. Oh, weight distributions may not be same at each point. If the weight distribution is not same at each point, so there will be the inductance variations. If inductance variations is there, obviously there are force variations. at each point. So the object will be either fall down or it will touch the coil. So this weight distribution should be. So I told you that spirit level accuracy is important with respect to the surface of the earth and with respect to the coil. Inductance variations is due to non-uniformity of the air gaps. So you can see that if air gaps are different at each point, so obviously the force will be changed. So again it will be fall down or it will touch the coil. Disturbances. So disturbances may be two types of mechanical disturbances, electrical disturbances. Mechanical disturbances something like that I told you, spirit level accuracy or true mechanical zero. That is the mechanical disturbances. Mechanical disturbances, suppose we touch the setup, so this will make the system unstable. Now electrical disturbances can arise from the power, from the circuits. Electrical disturbance from the sensors also, it can arise, from the controller also it can arise. This type of disturbances are there. Power consumption. So coil is consuming the power, so power consumption is a problem. Power capacity, that is the important factor of the actuator. Heating problem. So heating, so actuators we are using, that is the coil, the actuators, so that can be heat. So this can also create a disturbance, electrical disturbance. Sensor noise. Noise can arise, some fluctuations. If we see the sensitivity plot of the sensors, then we can check the sensitivity linear or non-linear, or something disturbance is coming or not. If external disturbance is report, then what is the nature of the system in the stability aspect. This type of check we can do. From control system aspect, the system is highly unstable system and nonlinear system strongly. Because of that, force and air gap profile is highly nonlinear. It will immediately touch the coil. An unstable system, because the one force, coil force is in upward direction and gravitational force is the downward direction. So unstable system. And another problem is the sensitivity to the parameter uncertainties. So parameters which we require for modeling purpose, that should not be proper. So there have some uncertainty. So we have verified the parameters uh, by three ways. First, practical parameters we have calculated. Yes, inductance we can easily calculate, get the inductances, and current also we can get practically. So then we have, what we have done, we have uh, through NC software, the electromagnetic analysis software, we have checked it through simulation. So simulation, practical, and third is process is the analytical model. Analytical model is fully mathematical. So Pohl's methods are used, where all the flux natures, how it is entering, how it is exiting, how where it is exiting, well, a full overall scenario of the flux. From the flux we can get the inductance profiles, permeance profile, etc. From that we can calculate all the practical parameters which we require for modeling. That three ways we can do, and we can test and check that if parameters are matching through simulation, practical and analytically or not. If not matching, then there have some errors, and then we should take care of that error. Linear approximation of the electromagnetic force. We are linearizing model at the particular operating point. So we are working not on the average model. We are working on the small signal model. So small signal model, electromagnetic force, we are linearizing. Actually electromagnetic force is the non-linear. We have linearized at a force, by force we are linearizing the model at particular operating point. That is also a drawback. So these type of aspects, control aspects, we have to these are the challenges. Unmodeled dynamics of the actuators, maybe the dynamic of the actuator may not be perfect. That type of problems are there. So systems should be robust. So systems should be robust. No parameter uncertainty. We'll have to minimize the parameter uncertainty. If we can consider this type of whole, we can take care of this whole challenges, then we can make the prototype robust, and parameter uncertainty will be minimum, and then the system would be stable. Otherwise the system, to make the system very difficult to make the system stable. So for the spherical object, we can say that that 3D view. So first, when we are trying to fabricate the setups, before that there are many process. First, the design of the coil, for selection of the object, mass of the object, then spherical object coil design is completed, then the frame of the prototype. So frame is a spiritual accuracy and true mechanical zero. Once these are completed, and then we have to do analysis, simulation, electromagnetic analysis first required. So from electromagnetic analysis we'll have to see the flux patterns, how fluxes are going, flux exiting, leakage flux, etc, etc, and the inductance profile, force air gap profile, current air gap profile, etc. We'll have to check through simulation, electromagnetic analysis. So electromagnetic analysis is very much important, because from electromagnetic analysis we will get the idea uh, to fabricate the setup. And then analytical model is important. Analytical model, this is the analytical model, how flux are entering and from the exiting from the core, and then it is passing through the spherical object, then steel frame, these few fluxes going by this way. So the flux patterns are shown in figure 9, and figure 10 it is showing that the electromagnetic analysis in software, how flux are exiting and entering. That the so flux pattern is not linear pattern actually, so it is distributing each and everywhere. So already told that leakage for the spherical object, the leakage is more, because they are not getting closed path, so flux are distributed here and there. This is the that we cannot do anything actually, because that though we have kept the steel frame, still the flux leakage is very much. So that's why the reason is that the coil is too big and the object is small, because not getting flux path, so maximum flux are actually misusing. So it is not generating force, so it is not generating actually inductance. So operating current is 0.6 ampere, means at the 16 millimeter, suppose, so which point we will more linear is the model, that is also will be decided from the analysis or the inductance profile. From inductance profile we will choose the operating point. What point is the possible operating point, what should be the possible operating point to make the system. Each and every point is not the operating point. Okay, if we take any point, then it is not possible actually. So we'll have to we'll have to choose a particular possible operating point from the analysis, electromagnetic analysis or inductance profile, and then at operating point we will take the all operating operating parameters. So it's a small single model, operating parameters. Operating current is 0.6 ampere, so 0.6 ampere we are doing FEM analysis, and then we will get the parameters. So parameters is the current air gap profile, inductance air gap profile, and the force constant is the one parameters that is required for modeling. Now please see the figure 12, that in the inductance profile, when when at 5 millimeter gap the inductance is more. Obviously when the gap between the core and the object is less, the inductance is more. Okay, where suppose imagine that the object is starting from core and it is going downward, so this profile will come, and at a particular point when gap is something like 20 millimeter from the core, then the constant inductance we will get. Okay, that constant inductance is nothing but the coil inductance. So so coil inductance, actually now no flux is entering through the object, we are not getting the inductance through the for the current, we are getting the only coil inductance. That coil inductance is fixed, So coil inductance is, so that the last one, suppose in 18 millimeter gap in figure 12, we are getting the fixed operating fixed inductance, that is the coil inductance actually. At this point they have no effect of the uh, coil. If we increase or decrease current, so no effect. So that is only coil inductance. In this joke, please see figure number 12. So 10 to 20 millimeter gap, there the inductance is almost constant. So in this zone we'll have to take the operating point. If we take the operating point too close to the core, then the instability is there, so it would be very difficult to make the system stable. In this zone, if we take the operating point, it will it will help to make the system stable. Force constant profile and the force air gap profile. So for a fixed current, actually current is non-linear in the we are doing this analysis in open loop actually. Okay, so in open loop the all the plots are in open loop. In closed loop current will be also non-linear. uh, After linearizing the model, the current will be fixed DC. So at 0.6 ampere, we are plotting the force air gap profile. Force air gap profile. Please see highly nonlinear system. So simulation result in figure 14, figure 15, and analytical and practical results. So analytical is fully mathematics. Flux patterns, from flux patterns we get the inductances, permeances, then we calculate all the parameters. Force will automatically, force is coming from the inductance actually. Okay, F equals to minus half I square dl by dz. So derivative of the inductance multiplied by the current square is the force. So we are getting this force. Now plus that practical, analytical and simulation. And when this analytical simulation and practical matches, then only you can take the plots. Otherwise if there are errors, so you'll have to take care that errors. So when it matches, then this is the perfect parameters. Otherwise there have a parameter uncertainty, and if there have parameter uncertainty, then if we take the parameters, then the modeling will be incorrect and the system will be unstable, controller design will not be correct. Now coil design for the object is also important. Coil design for these spherical objects, which are taken care of 16 millimeter as the operating gap. It is coming from the inductance profile. Okay, all the points are not operating point. So if we see that where there is constant zone, then only we can take the operating point. The other zone, and the system will not make the system stable. Now current rating is important. So how much current is required at the operating point? Suppose 0.9 ampere current is required, then you'll have to design the coil of 2 ampere, taking care of the few precautions, heating problem, power consumption problem, this type of problems are taken. So you'll have to take 2 ampere. Suppose here 0.69 ampere is the operating and current, so we have taken 2 ampere current rating. Number of turns, please see 3600 turns. Okay, so 24 is WZ wire gauge, etc. use. So coil design is the important part of the, because coil is the mother and the object is the child. So there should be a beautiful relationship, very beautiful relationship between mother and child, such that it will never become stable. Design specifications of object, we have chosen 62 gram spherical object. Air gap, we have chosen 16 millimeter gap. It is coming from the inductance profile. It is coming from the electromagnetic analysis that 16 millimeter is the approximate possible operating gap. At that point, it will make the system stable if we design the controller. And operating current, so at that operating point, what is the operating current at that point operating? So all are operating parameters at 16 millimeter gap. So it's a small signal model. So small signal model, so we are not working the average model like nonlinear control strategies, the sliding mode controller, etc. So resistance of the coil, Inductance of the coil, inductance at that operating point actually. Okay. uh, Sensitivity of the LDR when feedback it will be required. So force constant. So how we will linearize the model. So already we told, I told that to linearize the model we require the physics behind the circuits. So one force is in upward directions, one force is in downward directions, and they are have one acceleration of the object in free space. So that is the acceleration of the object m d2 del is the actually small signal. Actually it actually it is a small signal model is written here, but before that there have lots of calculations from average model how small signal model is coming. Actually using Taylor series expansion we linearize the model from non-linear model to linear model. So then delta z will come, not z will come. Z will not come, delta z will come, small signal model. So this is the acceleration at operating point, and two forces are there, on upward coil force and the downward force is the mg. So when it will be levitated, when mg will be equal to the downward force is mc, so mg will be equal to the coil force, then it will be stable, and we'll have to avoid the acceleration through controller. So if we model that, this equation number 2 will come after linearizing, because force is non-linear. So we will Taylor series expansion etc. is not in these slides. So after calculations and lots of linear approximation method, we will get this second number equation, and then taking Laplace transform we will get the second order system, where one pole is at the right hand side 14.5. So system is unstable system. Now nonlinear model is linearized at that point, uh, which we want to make the system stable. At that point the system is linear, so all the parameters has been taken at that point only. For ball it is taken 16 millimeter air gap, so that point that transformation has come. And this is the mechanical system, and the current because the coil is the RL circuit, so there have one electrical dynamics, and that is the first order system, stable system. So overall system is the third order system, unstable system. One pole is at the right side of the S plane. Now we'll go to the block diagrams of the system. So levitation system means the mechanical systems, means force air gap, force balancing equations. And second is the electrical system, the magnet. And here feedback is 1350, means sensitivity. From sensitivity plot we will get, okay, the LDR and light bulb sensitivity, and then we will have to design the lead compensator from the MATLAB or some simulation tools. We will have to design the system. So this is the overall closed loop system. You can check the root locus plot at overall gain 21. The system is become stable. So closed loop figure 17 shows the closed loop root locus plot, and DC gain is 21. DC gain we will have to put a pot variable resistance to adjust this DC gain. Frequency response of the overall closed loop system, so Bode plot. So you can see gain margin is 55.2 dB and phase margin is infinity. Sensitivity of the sensor is important. LDR and light bulb we have used, so full dark and full light, when we'll have to test at each point, keeping the object between LDR and bulb, we'll have to check the sensitivity, and from that sensitivity we'll have to take at operating point we'll have to take that feedback gain from the sensitivity table. Now we can test the when it will become the stable, means system is stable, means spherical object is floating, means controller is working excellent, and then you can take the waveform, the transient response. So we actually we required a fixed zero operating current. Okay, so transient response is this and steady state response is this. So steady state. So there have some ripple. Because of that, we know that 50 hertz ripple is there. Though we have in any power supply, you can see that there have some ripple. We cannot avoid that 50 hertz small amount of set the ripple is coming steady state response. You can see that the we predicted 60 millimeter 16 millimeter as the operating gap. Okay, but practically it is coming 13 millimeter. Practically it is levitating at 13 millimeter. Because of that, parameter uncertainty parameter uncertainty plays an important role. Parameter exact parameters, to get exact parameter is very difficult task to get. Though we have compared with the simulation, though we have compared with the analytical model, though we have compared from the practical results, all matches closely, but still there have some uncertainty coming at the output. That is the challenging job. Though we have design was perfect, we have taken care of all the precautions, and parameter uncertainty will surely come in any kind of limitation prototype. Parameter uncertainty error will surely come in any electromagnetic limitation prototype. Because we know we cannot see many things actually in the levitation. We cannot see many things what is happening inside the electromagnetic levitations. We cannot though we have taken care precautions in every point of aspects, but still there have some hidden there are some hidden and problems which we are not able to see from circuits, from sensors, from feedback, from controller, from parameter uncertainty, from design, from analysis, from fabrications point of view. There are some missing uh, missing data. And so operating current also is changing from 0.6 was predicted value at the operating point, but it is coming 0.45 ampere. Now we can see, so already I discussed on the spherical object. Spherical object is the center of mass, its equilibrium point. Now when the shape is changed, mass is also changed. So the coil will be different, and the core of the coil will be also different. For the spherical object, it was a I type core. Now it is a C type core, because the core, so we need the closed path of the fluxes. So we need the core shape will be changed. So the object is changed, mass object changed, the core coil structure will be changed, coil cores will be changed, number of turns will be changed, and everything will come from the electromagnetic analysis actually. Before going to the electromagnetic analysis, we cannot design the coil. So when the coil design is completed, means in the number of turns, current rating, wire gauge, etc., then we'll have to place in a fabricated prototype, and with supporting aluminum made true mechanical zero setups, and spirit level accuracy is required, because we are working against the gravitational force. Spirit level accuracy will have to keep the object also at spirit level, and and object and coil gap should be equally distributed. Coil core of the coil and the object, the gap between these should be equally distributed. So no, so this otherwise there will be weight distribution problem, or inductance variations problems, or air gap variations problems. So there also requires spirit level accuracy. Then we can design, and then we can do FM analysis using NC software, and then we can check the flux patterns, flux leakage, and then losses. Okay, there are some eddy current losses, etc., that also we can take we have to take care of. And then that inductance profile will come from the ANSYS, and from there we can take the parameter uh, required parameters. So one thing we will have to tell that for the spherical object there was only one sensor, LDR and light bulb, that was controlling on the Z direction. Now we record X direction, Y direction, and z direction both. So you can see that there have in figure number 20 there have lots of RLD phototransistor are placed, and below there have the one inductive proximity sensor. Below there have one inductive proximity sensor, and these three type RLD phototransistors pairs are and two, three, four pairs are there, and one inductive proximity sensor. So these all the sensors will be combined in a weighted gain combination approach, and then it will be given to the feedback. Okay, gain combination approach is also a different part of the feedback strategies that is used in Levitation, and this will be used in the feed as a feedback. So here you can see that the complexity many extra complexity will arises for the shape because of the center of mass is not the equilibrium point. So there will be many other problems. So weight distribution, air gap distribution, inductance variations, etc. Will be the another addition challenges in for the this object actually. But spherical object there was not this type of problems. So it was a spherical. If there are some disturbances, so there have some roll PCO etc. But it will rotate. It will rotate at the uh, operating point. But here what will be happen, it will become unstable and it will fall down or it will touch the coil. So this type of problem for the shape of the object. Now the we require the prototype should be spirit level accuracy because we are working against the gravitational force. So spirit level accuracy means the object will be placed at spirit level and coil also will be placed at spirit level. Then there will be chance that there have no weight distribution or air gap variations or inductance variations. Then so both will be at spirit level, object and the coil. So this setup also need two mechanical zero, means that it will not be affected by the outside fluxes. So outside flux cannot impact on that setup. So these type of setups cannot be made by hand. These type of setups is it can be fabricated by the central tool room, micro, small or medium enterprises. They can build this type of setup by hand. It is never possible. If we can try, then it is beyond our imagination that the system will be stable. It will never become stable because from the starting point, these are the very starting point of the setups. We are not going on the controller design. Now we are designing the platform. We are just making the uh, platform. So platform should be spirit level at each point and true mechanical zero. There should not be any kind of mechanical disturbances arises from the setup, and then we can and go. Once this completed, object is fixed, weight of the object is fixed, coil design is fixed, setup is ready. Now we can go for the practical parameterizations. We need parameters for the modeling. So we need parameters. Parameters can be evaluated by three ways: analytically, fully mathematics, that is used by Pohl's method, flux natures, flux patterns, flux leakage, flux linkage, etc. We'll have to take care. And then simulation, electromagnetic analysis, simulation software, and the ANSYS. And then third, the practical also at each point we can take the parameters. That three type of parameters, the three ways we can evaluate the parameters. Then if it matches, then we can go for the modeling. If it not matches, if there have some errors, then we'll have to rectify that error first, then we'll have to go the modeling. Now if parameterization is okay, then we can go for the modeling and stability analysis. Modeling and stability analysis. So So modeling means the physics inside in the setup. So one force is upward, one force is downwards, and acceleration is working at the free space. So this equations, actually this equation is will come as non-linear because force is non-linear. We'll have to linearize the model at the particular operating point, and which point it will come from the inductance profile. And inductance profile, we can see that the at the highest point the inductance is more, then it is slightly decreasing, and then inversely decreasing, and at the end it is fixed. Means the coil inductance. Means if we don't send any current also, we will get the coil inductance. So that is the that we get. Then now we'll have to linearize the operating point. So now when it is linearized, then we can go for the transfer function is domain. Now we'll get the transfer function. From that transfer function we will see that the one pole will be at the right hand side. System is unstable system, so we have linearized the model from non-linear model to linearized model. But the transfer we have linearized the model from non-linear to linear at a particular operating point. So it's a small signal model. It's not average model, so we cannot use non-linear control strategies here because already we have been linearized the model. Now we will have we will do the stability analysis, and we will design the controller, which kind of PID controller, lead compensator, lead lag compensator, which kind of controller is required for these objects. We will check the different type of softwares, MATLAB, etc. Now we'll on now once we will check the phase margin, gain margin of the uh, system with the controllers. If we have kept phase margin as 30 degree and gain margin is 60 degree, so this is the best control strategies, control specifications, that phase margin is 30 degree and gain margin is 60 degree. And then we have fixed, the controller is fixed. Now we'll have to go the design of the analog controller, and then the testing of the associated circuits, and then experimental results. So, so for this plate levitation prototypes, this type of steps are there. So first, analog controller based levitation prototypes ready, and then FEM based analysis. So FEM based electromagnetic analysis. From there, that we will get many ideas how to get the parameters, and then parameter evaluations, all the parameters conducting parameter evaluation, and then parameterizations means all the plots, and then modeling means at we will choose a particular operating point, the inductance point, inductance operating point, and then at inductance at particular inductance at a particular operating point, we will choose all the parameters, and then we will put these parameters in the uh, equation, and we'll model the systems, and then we'll go for the Laplace domain stability analysis, and we'll check the control strategies. And then when controller is ready in simulations, then we will implement in hardware in the practical system. And then when control is ready in and simulation, then we will go for the hardware. Means we'll have to design the circuits through first the Vero board, and then breadboard, and then soldering, and then PCBs. So this is the, then we will perform the experimental waveforms. So analytical modelings I am going to discuss now. So analytical model is the flux patterns. Please see there have 1 2 3 4 5 6 zone of fluxes for the flat plate, and in shifted case actually with the, please see that we have shifted x amount, and please see the flux patterns, fewer straight line, fewer bending, and that is called the Bose method. And we will have to take care all the bend fluxes, and we'll have to take care the, so it's a huge integration. So we'll have to integrate all the cross sectional area of the flux surface, or we will have to integrate all the surfing of horizontal surface, sorry, vertical surface. So cross sectional area we will have to calculate through integration, and then we will get the inductance profile obtained through analytically, experimentally, and simulated. Okay. Oh, we can get the permeances here. Yeah. So please see P1, P2, P3, P4, permeance 1, permeance 2, permeance 3, permeance 4. Okay. And these are parallel to the permeance entering to the other arm of the core, so that we will get the inductances. uh, so we know that permeance are, when permeance are parallel, then we will get the reluctance in this way. So we will get the inductances, and if we get the inductance, we can check the inductance plot for the displacement in the x direction. uh, I think I will stop now. I will go uh, the next discussion in the next PPT. Okay, and the next discussion will start from here only. Okay, thank you very much for listening. Okay.